Now, the vector W is in the span. This is the definition of span. It's within the span of two vectors v1 and v2 if and only if there exists c1 and c2, which are kind of automatically regarded to be constant real numbers. If they're anything but real numbers, we need to specify it right here. So we can say c1 and c2 are rational numbers, or c1 and c2 are complex numbers. But if they're real numbers, we're going to kind of make the convention that we just have to say c1 and c2. As long as we don't put an arrow over them, we know they mean numbers, and they could be any real number. Okay, c1 and c2 such that, this means such that, c1 v1 plus c2 v2 equals w. In other words, there's something we can multiply by v1 and something we can multiply by v2, so that when we add these, we get the vector w. If that's the case, then w is in the span. Another way of saying that is then that w is a sum of multiples of v1 and v2. So we got v1, we got v2, we can go a certain distance along v1 and then a certain distance in the direction of v2 and get w, whatever w happens to be. Okay. Well, we're given vectors for v1 and v2 and w, and we're asked if w is in the span. So we write down this equation again. That vector now is, instead of just plain old w, is w1, a specific vector w1, which is equal to the column vector 5, 1, negative 1. Okay, the vector v1 is 3, 2, 4. The vector v2 is negative 2, 1, 5. So this equation becomes c1 times 3, 2, 4 plus, that's the v1 vector, plus c2, replacing the v2 vector by its components, negative 2, 1, 5, equals the w1 vector, which is 5, 1, negative 1. And it's exactly the way it's stated in your document. It's clear what v1, v2, and w1 are. So when we simplify this equation, we multiply c1, we multiply this vector by c1, and so we get 3, c1 times 3 gives us 3c1, 2c1, 4c1. That should be very straightforward. We've done that in other classes recently, and you've seen that if you've watched the notes. And then c2 times this vector gives us negative 2c2, 1c2, and 5c2. And there's a 3 in there. It doesn't belong. Okay. And that's got to equal the vector 5, 1, negative 1. This, in turn, can be translated. There's a step that I didn't do here because we've done these steps step by step. But the next step is to add this and this, which gives us one matrix, 3c1 minus 2c2 in the first row, 2c1 plus c2 in the second row, 4c1 plus 5c2 in the third row, and that's got to be equal to the vector 5, 1, negative 1, so that 3c1 minus 2c2 has to equal 5, 2c1 plus c2 has to equal 1, 4c1 plus 5c2 has to equal negative 1. Okay, well, this gives us an augmented matrix. We could also write it as a matrix equation. We don't get a square matrix, so we can't think of inverting the matrix. In other words, the matrix that we get from these coefficients would be a 3 by 2 matrix instead of a 3 by 3 or a 2 by 2 matrix, and we can't invert that, so there's no point in writing this as a matrix equation, at least as far as getting the solution. We instead write it as an augmented matrix and reduce that matrix. Well, you can do it yourself. This matrix reduces to this. Reduce it yourself if you don't believe me. And it reduces rather easily. This tells us what? Tells us that C1 equals 1, C2 equals negative 1, and it tells us that 0 equals 0. Now let me digress a second. If I'd have just chosen 3 random numbers over here, there's very low chance that this would reduce, that this last 0, that you would actually get this last 0. If this number was anything but -1, you wouldn't get a 0 there. Okay, so this number has, if these numbers are 5 and 1, this has to be -1 in order to get a 0 there. So even if I'd have chosen the first 2 numbers the same, if I chose the third number any different, it wouldn't work. Okay? And if I don't choose any of the numbers the same, it's just highly unlikely that the last row will just coincidentally cancel out. And then you would get 0 equals something that isn't 0, which can't be true, so there would be no solution. There would not be any C1 and C2 that make this true. Okay, so we verify this. So C1 equals 1, C2 equals -1, assuming the matrix does reduce to this. Once more, you can check this yourself. And I'm not sure you can really see that bottom line, so let me give you a little more room there. Okay. Then we can write C1V1 plus C2V2 equals 1, I'll put the 1 in there, I didn't before, 1 times the vector V1, the 3, 2, 4 vector, plus C2V2, that's -1, times the -2, 1, 5 vector, the V2 vector. Okay, we add those. Well, first we multiply through. 1 times this one just gives us the same thing, 3, 2, 4. -1 times the -2, 1, 5 gives us 2, -1, -5. Okay, then 3 and 2 make 5. It almost looks like a 3. I mean, it really is a 5, but let's make it look a little more like a 5. It fooled me for a minute. 2 and -1 is 1. 4 and -5 is -1. This gives us 5, 1, -1, which is what we hope to get. So we did find C1 and C2 that make this so. So W1 is in the span of V1 and V2. So I'll write that down. And officially, this is a set of vectors, okay, the span of a set of vectors. So if I wanted to write this just a little more precisely, I would have put braces around it to make it a set. Okay, so we've established that W1 is in the span of V1 and V2.